Hi math students, it's Mrs. Marcellus, and Barkamedes is with me again today as well. In this lesson we're going to find the surface area of rectangular prisms. Today's learning objective is, students will find the surface area of a rectangular prism by deconstructing the figure and applying a formula. Before we proceed with calculating surface area, first there's some important vocabulary we need to know. The first word is rectangular prism. This is a three-dimensional figure with two parallel bases that are congruent rectangles. Surface area is the number of square units needed to cover the surface of a three-dimensional shape. To find the surface area, it's often handy to use a net. A net is a two-dimensional representation of a three-dimensional shape. Here is an example of a rectangular prism and its net. As you can see, the box has been unfolded. And with every rectangular prism, we'll have opposite sides that are congruent. This is going to be really helpful in helping us find the surface area. What do you say, Barkamedes? Shall we go ahead and see if we can figure out a formula for calculating the surface area of rectangular prisms and then give it a try? Okay then, let's proceed. The surface area of a rectangular prism with length L, width W, and height h is the sum of the areas of the faces. The official formula for surface area is 2 times the length times the height plus 2 times the length times the width plus 2 times the height times the width, and we will use a label of units squared. We will use a label of units squared because we are taking a three-dimensional object and flattening it out into a two-dimensional shape. We are then covering the surface of that two-dimensional shape with square units. If we take a look at the figure below, we can see how the formula is derived. When we're working with rectangular prisms, the opposite sides are congruent. Therefore, we need to only find the area of either the top or the bottom, either the front or the back, and either one of the two sides. Then we can multiply each one of those things times 2 because there are 2 of each piece. Since a rectangular prism can be turned any direction, we don't have to worry too much about which sides we label with length, width, and height. We just have to make sure we account for the areas of all the pieces. Let's take a look at some examples. In this example, we're given a net of a rectangular prism. All we need to do is find the areas of the different rectangles and add all the pieces together. Let's start with the side pieces, the two blue squares. Each has dimensions of 10 inches by 10 inches, so each has an area of 100 inches squared. Next, let's calculate the front and back, the green rectangles. Each has dimensions of 10 inches by 15 inches, so each has an area of 150 inches squared. Next, let's calculate the area of the top and the bottom. We can see that one side of the rectangle is 15 inches, and if we look to the other end of the figure, we see the second dimension is 10 inches. Both the top and the bottom also have an area of 150 inches squared. To find the total surface area of the figure, we can now add all the areas of the individual rectangles. When we do this, we find the surface area is 800 inches squared. This is just one way to find the surface area given the net like this. There are certainly ways you can combine the measurements to reduce the number of rectangles you have to find the area of, and you also could use the formula, but quite honestly, I think this is the easiest way to solve this. In this problem, we'll start with the rectangular prism. One way to find the surface area is to draw a net of the figure. Then you can transfer the dimensions from the rectangular prism to the net to calculate the area. Let's start by finding the area of the top and bottom of our figure. Both have dimensions of 6 feet by 3 feet. We can transfer these measurements to our net and calculate the area. 6 times 3 is 18, so both the top and bottom have an area of 18 feet squared. Next, let's take a look at the sides. We can see that the sides have dimensions of 3 feet by 10 feet. We can add these numbers to our net, then multiply 3 times 10 to get an area of 30 feet squared for each side. Finally, let's find the area of the front and back. They both have dimensions of 6 feet by 10 feet. We will add these to our net, then multiply 6 times 10 to get an area of 60 feet squared. Then, to find the total surface area, we need to add up all the pieces. You can do this in multiple ways, but no matter how you go about it, you'll end up with a total surface area of 216 feet squared. How many square inches of wrapping paper would be needed to exactly cover this box, bow not included? To calculate this, we could draw a net like we did in the last example. However, it's probably not the most efficient method or something you'd want to do every time. Let's try using the surface area formula. To use the formula, you will first need to label the length, width, and height. Then you can plug those values in and calculate the surface area. We have 2 times the length times the height, which would be 24 and 14. This equals 672. Then you'd have 2 times the length times the width. This would be 2 times 24 times 11, which equals 528. Then finally, you'd have 2 times the height times the width. 2 times 14 times 11 equals 308. To find the total surface area, we will add the 3 calculations together. The final result is 1,508 inches squared. Using the formula works just fine, but it can be difficult to keep track of all of the letters and dimensions and which numbers to plug in where. When I do these problems, I try to streamline the process a little bit. Basically, we have to multiply each of the dimensions times each other and double them in order to get the surface area. I actually apply what I call the loop-de-doop method. I know it sounds silly, but drawing loops helps me keep track of which dimensions I've already used. I know I'll need to multiply 24 times 14 to get the front and the back of the box, so I draw a loop like this when I do the calculation. Next, I need to multiply 14 times 11 to calculate the 2 sides of the box. Therefore, I'll draw a second loop. Since I've completed those 2 combinations of numbers, that leaves me with only 11 and 24. This will be the top and bottom of the box. Then I draw my third loop. Now all the numbers have been accounted for. This will give me the same result as applying the formula without having to keep track of all of the letters and which dimensions they match up to. Another way you might approach finding the surface area is to, instead of multiplying each part by 2 as you go along, find the area of the 3 parts, then add them together and multiply by 2 at the end. You would find the area of either the front or the back, either one of the sides, and either the top or the bottom. You would then add those 3 areas together and multiply by 2 to account for all 6 sides. You will get the same result either way. It's really just a matter of personal preference. There are lots of different options when calculating the surface area, so you will need to apply which method works best for you. What is the surface area of this cube of cheese if it has a side length of 7 millimeters? The word cube is key in solving this problem. A cube has 6 congruent square sides. Therefore, the length, width, and height will each be 7 millimeters. To calculate the surface area, we could plug the numbers into the formula or use the loop-de-doop method, but those won't be the most efficient ways for a cube. We can easily find the surface area of a cube by applying our knowledge that all 6 of the sides are the same size. All we have to do is find the area of one side and multiply that by 6. Since all of the dimensions are 7 millimeters, to find the area of one side, we multiply 7 times 7. This gives us 49 millimeters squared. Since there are 6 sides, we then multiply 49 times 6. The total surface area of our cube of cheese is 294 millimeters squared. What's that, Archimedes? Yeah, you're right. What we've learned in this lesson will be helpful in completing the project we've been wanting to get started on. Archimedes has been telling me for a while now that he wants to paint his house. And since we know how to find the surface area of a rectangular prism, now we can easily calculate how much paint we need to buy. Why don't we go do some measurements and get started? Well, we've got work to do, so we're going to say bye for now, math students.